Morning and welcome to Physics Lesson 5.01 on finding net force and coordinate systems. This is the first video for this chapter. So in the last chapter, we went over Newton's laws and kind of the qualitative aspect. And this section, we're doing the quantitative. You'll notice that next to the topic, it has the homework sections. And 501 actually gets you set up to do the homework in 501, 502, 503. 501 is review, and it's how to find net force. This is what you did back in chapter 3 when you had the multiple vector problems. But in case that was a little difficult for you and you wanted some review, you can do this. This one's super optional. So this really more applies to 502 and 503. The first thing we're going to do is we're going to work on finding net force, setting up our coordinate systems, and determining, sorry, the dog, I am house sitting or puppy sitting my mom's dog, and he is running around. Hold on, got to pause the video. Okay, I'm back. Yeah, he already got into the cat's food, ate the cat's medicine, and I had to call animal poison control. So, shh, don't tell my mom. I think he's going to be okay. All right, so what are we doing? Yes, we've got, so we're starting off with just kind of looking at how Newton's second law comes into play with net force. And we're going to do 3 problems in this module, time allowing. So we've got Mo, Larry, and Curly pushing a 752 kilogram boat that float next to a dock. So let's do part A first. And we're going to go with pretty much standard coordinate systems. So we've got all 3 of them are pushing the same directions. We've got, let's say they're all pushing this way. And each of these is 80.5 newtons. That's an 8. Well, then we understand that the net force would be 80.5 plus 80.5 plus 80.5. And so I have a net force of, when I add that 80.5 times 3, I get 241.5 newtons. And this is my net force. This would be force 1, force 2, force 3. And when we're talking about the acceleration of an object, we always need the net force. Now, this one was super easy because they're all going in the same direction. We know that F, and we're going to start writing F net is mass times acceleration because we're going to have to specify which force we're talking about. Wow, this is really blurry today. I'm going to try to fix that. I don't know if that helped or not. So that gives me 241.5 equals 752 acceleration. It gives me an acceleration of 0.321 meters per second squared. All right, what about part B? So we have Larry and Curly are still pushing this way, but they're pushing in the opposite direction as Mo. Well, this is still 80.5, but this is going to be positive 80.5, positive 80.5. This one's negative 80.5. So now my net force is just going to be 80.5. So when I solve for this, I have 80.5 is 752 A, and A is going to be 0.107 meters per second squared. I probably carried, no, I had 3 sig figs. As I say, I probably carried that out too far, but it's okay. All right, here's another one that's pretty simple. A child pulls an 8-kilogram wagon across a frictionless surface, and you'll notice we're going to see this a lot, frictionless. So we're not going to handle friction until halfway through the chapter. With a force of 10 newtons at an angle of 30 degrees to the horizontal, find the acceleration of the wagon. So we're going to want a free body diagram. And I have, so now I want to make sure I put in both the coordinate system and my motion vector. So, and it says I have acceleration. So that tells me that, I'm going to be using probably F equals ma. All right, so I have my weight vector, got my normal force, and I have got a 10 Newton force at a 30-degree angle. Okay, I'm going to redraw that 10 Newton force. Let's redraw that. So this is the first problem where we need to do motion analysis. My motion, which is a little off screen, and I always do it as a green arrow. Sometimes I might write some notes above it, like what's going on with the motion. With this motion, that's a W with acceleration. So what forces are going to contribute to this acceleration? Only the forces that are in the direction of the motion. So in this case, this is we're going to call this FA for applied force. I'm going to have FAX and I'm going to have FAY. Only FAX contributes to motion. I'm not moving vertically at all. I'm only moving horizontally. So that means in this case, I have FAX equals mass times acceleration. Well, I know FAX is going to be 10 cosine 30. That's going to be positive. That's going to be equal to 8. And I'm going to have an acceleration when I solve. It's going to give me an acceleration of 1.08 meters per second squared. Now, I want to point something out. You might be looking at this free body diagram and saying, you drew that wrong because your weight vector and your normal force aren't equal and opposite. No, but my vertical forces are. What you may not have noticed. So my upward, so all of the vectors that point upward have to equal this. This guy's about what? That long. So these are not equal and opposite, but is this the only upward force I have? It's not. Don't forget about FAY. If I take that vector and that vector, those two added together are equal and opposite to my weight vector. So this ties back into what I talked about where you have to do the motion analysis. And there's a lot of problems where they'll say solve for the normal force. If I was going to solve for the normal force here, I would have to take into account both this piece and that piece to find the normal force. But that's down the road a bit, so I just wanted to point that out. Okay, I'm going to pause and switch my papers to the next sheet. Okay, we're ready to go here. You'll notice I had to write in, I had a typo. I didn't want to reprint the paper, so I just corrected it, and then you'll get a corrected version. Two men are trying to dislodge a rock with a force of 55 newtons at 40 degrees and 35 newtons at 30 degrees. So I put my degree sign there. So let's start off before we draw our coordinate system. So we've got a little bit of a different scenario here. In the other ones, we had three guys go in the same direction, and we had a girl pulling a wagon. So the girl pulling a wagon, it made sense, and most of our free body diagrams have been from the side. But in this case, if you can imagine if you guys were if your car was stalled, and you and your buddy were back and you were kind of both on angles and you were trying to push the car forward while a third friend was trying to steer. Think about how you're going to orient that. So I'm going to do this in pencil because I'm going to erase this. So don't draw this. But if you were going to try to draw a free body diagram like that, you'd have to do a three-dimensional axis, and you'd have to show one person coming in this way and one person coming in this way, and it's going to get really, really messy. So sometimes it makes sense. That didn't show up at all, did it? Okay, well, let's see, three-dimensional. I'll erase it here in a second. So you have to try to bring somebody in here and somebody in here, and it just doesn't work very well. What works better for this kind of scenario is to do a bird's eye view. So we're going to do what I call a bird's eye view free body diagram. So here's the rock, and we're going to go with a bird's eye view. And we're going to draw our axes then down through a horizontal plane. If this is anatomy class or you're in my anatomy class, we would call this a transverse section. So then we're going to have one guy so if you're pushing on the rock this way, your vector would go here. And this one is the 40 degree is 55 newtons. And the 35 Newton is 30 degrees. So I need to draw that a little shorter and with a little less of an angle. And we're going with 35 newtons. And the problem says find the resultant force and the acceleration. So I'm going to have motion. So let's go with this coordinate system. Say my motion is this way with acceleration. So I'm going to redraw these vectors nice and big. So let's do our 55 here. We'll call this force applied 1, and it's 55 newtons at a 40 degree angle. We would call, we have to be careful here because these really aren't horizontal vertical vectors. So this is going to be force applied 1 x. This is going to be force applied 1 y. And let's do my 35, a little shorter. I've got my force applied 2x, and we'll call this force applied 2. It's 35 newtons. Force applied 2y. Well, so now we have to do our motion analysis. Which of these vectors is contributing to motion? Well, if my motion is this way, is that guy contributing to motion? No. The ones that contribute to motion are this one and this one. And guys, this is a step you can't skip. You have to do a motion analysis. Well, this guy is going to be positive. It's in the positive direction. We're going to take 55 cosine of 40. And this guy is going to be positive 35 cosine of, what was my angle again? Whoops, I have a typo. 30. You were wondering, uh-oh, am I going to catch that as a teacher mistake? So this should be 30 cosine 35. Notice I didn't do this in unit vector notation. Some problems it's easier to do it in unit, or to write everything into unit vector notation and to write it out from there. But in this case, I really am not concerned about these other vectors. So I'm just going to do this. This one's going to be 30.3. So I've got 55 cosine 40 is going to give me 42.1. And 30. 35 newtons. Oh no, I was right the first time. By golly. Okay. But it's a good illustration how easy it is with a, just looking at something the wrong way. There we go. You kind of look at it wonky and all of a sudden you've written in wrong values. Now on a test, that would maybe be a half a point, if anything. All right, so I should have kept it where it was the first time. So I've got 35 and 30. So we've got 35 cosine 30 is going to be 30.3. I'm going to add these up to get my net force. And when I add those up, I'm going to have 72.43. Remember, carry out, I should have carried out an extra digit here. Carry out extra digits and then round at the end. So this is my net force, and that's going to be equal to the mass of my rock. So if we want the acceleration, I'm going to have 68 kilograms times A. And when I solve for A, I'm going to get, I didn't write it down. Okay, I thought I had all my algebra worked out, but I had not. So I'm going to get 1.07 meters per second squared. So it seems like that's a very common acceleration. All our problems ended up with about the same acceleration. So here we go, part B. How much time does it take to move the rock 20 meters? You need to develop in your brain a set of an alarm. And anytime you start seeing kinematic variables, I've got displacement, I've got time, it's a pretty good bet you're going to have to do a kinematic equation. So here we go. For part B, I want to know how much time. So let's do, we're going to need V sub O, V sub F, X sub O, X sub F, A, and T. So I'm solving for time. I found out that my acceleration, it's going to be positive. It's positive 1.07 meters per second squared. How much time does it take to move the rock 20 meters if it's starting from rest? All right, the formula that I think is going to work best for me is, let's do X sub F equals X sub O plus V sub O T plus 1/2 AT squared. So this is going to be 20. This term is going to be 0. This term is going to be 0. It's going to give me 1/2 times 1.07. And that's going to be T squared. When I solve for T, I get 6 seconds. Get out the, if you have it with you, get out the diagram that I gave you back at the beginning of the year. And what we're going to have there is you're going to see that we have kinematics, and it goes to newtons, and then it goes to work energy, then it goes to momentum, and it comes back around to kinematics. So what we're doing is we're starting to work that circle where we're beginning in kinematics and now we're in newtons. So we're working here, but we have to work our way back, and these arrows go both ways. So we're starting to work the circle. That's why I never worry really about reviewing, because I know everything that you did at the beginning of the year will come back around later. All right, that's our introduction. That should get you started on some of the homework sections. Thanks for watching. Have a good day.